one, I'd like you to first of all record in that space next to it, t-tests in general. T-tests in general. So the material I'm going to be giving you today for the next, I don't know, probably 10 minutes or so, is going to be largely just general information about t-tests and how we can distinguish them from other kinds of inferential statistics. So why don't we take a look at what t-tests are all about in general, okay? So you've written down t-tests in general, okay? First thing you need to know about t-tests is, hey, no surprise here, they apply bivariate analysis, or as you knew from chi-square, two variables. So again, we're talking about an inferential statistic that applies a bivariate analysis, which means it's using two variables at all times. Later in the video, you're going to see why these two variables are, in fact, very different than the way we used variables in chi-square, but we'll get to that, okay? First thing to know, t-tests apply bivariate analysis. Next thing to know, they are inferential statistics, which, big surprise there, not a surprise at all. So you already learned from the hypothesis testing unit and also when we did the application of chi-square that anytime you hear about statistics being inferential statistics, you're most likely, in fact, all the time, going to be using some kind of a hypothesis testing. And there is really no change with respect to that between chi-square and t-tests. But there is something with regard to language that you must know, okay? So we're going to look at the first letter. I need you to know that when we are talking about t-tests, unlike the way we wrote the null hypothesis for chi-square, t-tests are written a little differently. They read, instead of reading there is no correlation, association, relationship, they are actually a test for difference among variables. That's what makes t-tests unique from chi-square and also correlations. We are looking for differences between the variables that we're applying the t-test unto. So the first thing you need to know is that the null hypothesis for a t-test reads, there is no significant difference between. That's how the language reads each and every time you write a null hypothesis for a t-test fact pattern. So make sure you write that down under A, okay? Well, I guess next to A. Let's take a look at B. Another characteristic that you recall from inferential statistics in general, and then also we applied it in chi-square, is when we're doing an inferential statistic, if we're doing it by hand, by and large, we are going to compare a calculated value and a critical value, and that's no different here. We're going to compare a calculated t-value against a critical t-value to test the null hypothesis when we're using statistics with t-tests. So again, if you take a look at letter B on your paper, you can go ahead and write next to it, compare calculated versus critical t-values to test the null. Okay, so you know that already now. For letter C, calculated t-values are absolute values. Does not matter if negative. Okay, that's different. That's kind of new, isn't it? When we were dealing with chi-square, we really weren't seeing any calculated values that were negative. That's different with t-tests. With t-tests, we are going to see negative values, but the only thing you're concerned about is the absolute value of the number. So if it says negative 23.06, we don't care that it's negative 23.06 when we're measuring it against the critical value. We just want to know whether or not it's bigger in terms of its absolute value. Many of you might recall from earlier classes you had, maybe in junior high and high school, anytime you have a value, whether it's positive or negative, between two lines, it's referring to the absolute value of the number, which means its inherent value regardless of whether it's positive or negative. So when we're talking about calculated t-values, we're going to recognize them as absolute values. It doesn't matter if they're negative, okay? Next, for number 3, t-tests, unlike other comparisons, which we're going to look at, specifically ANOVAs, they compare the means or averages between only two groups. Okay, now the groups themselves may be two samples, or the groups may be a whole population against a sample that was taken from it. We'll get to that. But you must remember that with t-test, we're only looking at a comparison of the averages between two groups. If we went beyond that, you're going to have to use a different statistic. Like I said earlier, maybe an ANOVA. Okay, so that's what you need to know. That's the third point I wanted to make today on that point. Number 4, and you're going to notice that there are some small letters below number 4 as well. T-tests come in 3 varieties. Okay, these are the 3 kinds of t-tests we'll be looking at in this class. Number 1, letter A, the one sample t-test. Okay, we'll talk about the one sample t-test a little bit more today. Next is the 2 sample independent t-test. What do you need to pay attention to here? Well, there's 2 samples and it's independent. You're going to know what that means most likely before the week's up. And finally, we're looking at, in this class, the 2 sample dependent t-test. So again, the things to pay attention to, it's 2 samples, not just 1, and it's dependent, which again, you'll know exactly what that means. But for now, you just need to know that t-tests come in 3 different flavors: 1 sample t-test, 2 sample independent t-test, and 2 sample dependent t-tests. Okay? Take a look at my next slide. Okay, characteristics of variables. This is Roman numeral 2. Up to this point, when we studied, for example, chi-square, which is really the only inferential statistic we've looked at so far, the level of measurement was uniform. In other words, it didn't change across the variables. So when we were looking at any set of variables for a chi-square, they were all nominal levels of measurement. But that's not the same with t-tests at all. So what we're going to have to keep in mind is this. This is the first time we're kind of making a distinction in this class between independent and dependent variables. Let's take a look at number 1. The independent variable is at the nominal level of measurement, okay, whereas the dependent variable is at the interval ratio level of measurement. Now, you might be saying to me, oh, okay, well, so we do have to distinguish between independent and dependent variables. Yeah. And they actually are going to come in 2 different levels of measurement. That's the first time we've seen this, and really one of the only times we're going to see it in this class. You're going to get more familiar with this as we go along. It's not going to be a big shock to you. Bottom line is I just need you to kind of pay attention to the fact that in t-tests, we will be looking at 2 variables because, again, bivariate analysis, there's going to be 2. One of them will be characterized as the independent variable. That one will be nominal level of measurement. The other one will be naturally the dependent variable, and it will always be at the interval ratio level of measurement. So things you absolutely need to know for this particular unit going forward. Okay, so you're writing those down right now. I can tell you're writing those down. I can't really hear it, but I'm imagining you writing this down. Okay. The next thing, and this is where students can get a little tripped up, but not you guys. I think you're going to make it through this okay. It's just a matter of being able to slow down with trying to understand it. Besides comparing calculated and critical values to find out whether or not to reject a null hypothesis, there's another way you can do it, and that is through p-values. Okay, so that's Roman numeral 3 today is p-values. All right, so go ahead and write down p-values. And actually, the p in p-value stands for probability, which again, didn't we do a unit on probability and hypothesis testing? And yes, we did. P-values stand for probability values. And if you're doing any kind of an analysis with variables on a computer system like SPSS and even Excel, a lot of times they won't give you, in fact, they never really do give you the calculated versus the critical value. They give you just a p-value. And what you're supposed to do with the p-value is figure out whether or not you're supposed to accept or reject the null hypothesis based on the p-value. So it's a little bit of a shorthand for calculated versus critical. All of this is going to make a lot more sense in a couple of minutes, so just bear with me. Let's keep going with the p-values. Here it is. P-values or probability values are another way to test the null hypothesis. Okay, again, It's kind of shorthand for what I just said a minute ago. P-values or probability values show up quite a bit, like I said, in computer programs. And anytime you're looking at research, you will frequently see a p-value. They won't typically list in the analysis itself the calculated and critical values. You can kind of just extrapolate it from the p-value. All right, so let's take a look at what the next one is. When a p-value is 0.05 or less, we reject the null. Do I need to push the button again? There it is, hypothesis. When a p-value is 0.05 or less, we reject the null hypothesis. So I guess you can probably figure out what I'm going to say next, huh? Well, let's test your understanding. When a p-value is greater than 0.05, we accept the null, there it is, hypothesis, all right? So the 0.05 line is really, like I said, a shorthand for determining whether or not to accept or reject the null hypothesis in the same way that you used a calculated value against the critical value. Now, you may be saying to me, well, why are we using one? Why can't we use both? Truth of the matter is you can. And I left a space on your sheet for you to fill in something that every year I find students find helpful to help them keep all this straight. So I'm going to go ahead and flip to the next slide here in a moment, but I'll give you another moment to write things down, okay? Let's take a look then at the next slide, and I guess you could even pause if I'm going a little fast. So sorry if I'm going fast, but I'm going to go ahead and hit the slide. Okay, so this is it. This is what I wanted to show you. This is kind of something I came up with a number of years ago that has helped classes of students I taught kind of keep it all straight. So let's just take a look at what it says here. Here it is, you reject the null hypothesis. So this column is going to be the null hypothesis column, and the two things we can do with the null hypothesis is reject or accept. So if you have, as we've learned in this class so far, a calculated value, and you find that the calculated value is greater than the critical value. So again, for this column, we're going to be looking at a comparison of the calculated versus critical values. See the little alligator mouth? That's what they used to say to me in 5th grade. So, okay, if the calculated t-value is greater than the critical t-value, of course we're going to reject. That's what we learned, okay? But then you also get to incorporate what I just said a moment ago about p-values. If you get a p-value that's less than or equal to 0.05, you will also reject the null hypothesis, okay? All of that is reversed when you get down to the accept row. So for a null hypothesis, we will accept it if the calculated t-value is less than the critical t-value. You can see me, I'm kind of bouncing around with my cursor. Hopefully that is showing up pretty clearly for you. The calculated t-value is less than the critical value. Of course, you would accept the null hypothesis, but then also we're adding this column here. If the p-value is greater than 0.05, you're also going to accept. So really what we have here are just two ways to decide what to do with the null hypothesis based on whatever you're doing. Now, if you're doing things by hand, you're going to find a calculated value. You're going to find on a chart a critical value, and you can reject or accept based on a comparison of your numbers. If you're running Excel, if you're running SPSS, if you're running any kind of a statistical analysis by computer, it's probably going to be giving you a p-value. And if your p-value is less than or equal to 0.05, you're going to reject. But if the p-value is greater than 0.05, you're going to accept. All right. Hopefully that makes some sense. And hopefully my cursor has been illuminated for you. I'm going to try to put that effect on for you to see if that spices things up a little bit. Okay. All right. Hopefully by now you've been able to complete the little grid that I gave you on your participation sheet to kind of help move you along and get you where you need to be. Hopefully that made a lot more sense, because frankly it can get pretty confusing if you don't have something to kind of help tie it all together. That's why I made this chart for you. Okay. Hopefully you had enough time to look it over. Let's take a look at the next slide. All right. One sample t-test in general. Let's talk about the one sample t-test in general. it compares the X bar of a sample. So we already know that the X bar goes with the sample to the actual or theoretical mean, which of course we call the mu, from the population from which it was drawn, and the it in this case is the sample. So compares, let me read it again, compares the mean, or in other words for the sample, the X bar, to the actual theoretical mu from the population from which the sample was drawn. So we're comparing a mean of a sample to the mu of the population from which it was drawn in order to determine whether or not the sample is different from or the same as the population from which it was drawn. Now we're getting into that language again about there is no difference. Remember how I told you set up a null hypothesis for a t-test saying there is no difference? Well, now you can kind of see how that plays out. If we have a sample mean from greater population that is the same, well, bottom line is we can say this sample kind of represents the population. However, you may find that you will have to in some cases reject the null hypothesis and find that in fact there is a difference, or there's no difference at all, depending on how the numbers shake out, and that's going to be your t-value. So I think that what you want to remember with a one sample t-test is it's one sample being taken from a larger population, and the question we're asking ourselves is how alike or how different is this sample that we took from the population from the actual population. And we're doing this by measuring the means of the sample against the mean of the population, which we'll call the mu. And we're getting a t-figure or a t-value to determine whether or not to accept or reject the null hypothesis. And as you remember from earlier, the null hypothesis for t-test is there's no difference. Okay, so if we accept the null hypothesis, we're saying, yeah, there's really no difference between this sample and the population mu. Whereas if we reject the null hypothesis, we're saying actually there is a difference between this sample and the population mu. But don't worry. And if you have to play this back a couple of times to hear me say it a few more times, that's fine. But we'll also be practicing this over the next couple of weeks in pretty great detail, like we did with, as you recall, normal distribution, z-scores, method 1, method 2. I mean, all of this makes sense to you now, hopefully. All right. Next point, this is number 2, recall that whatever characteristic is studied, okay, is called, what do you call it? The parameter within a population. Remember that one? We call anything that's being studied, whether it's homelessness or it could be diabetes, it could be anything really in a population. We're going to call that characteristic a parameter. And the same characteristic is called the statistic when referring to a sample. Now, I didn't make any of this up, okay? Don't hate on me. I didn't make any of this stuff up, so I probably would have used different language than any of this. But you know what? We have to go along with it because it's here. So just a reminder about how this is supposed to look. All right. Next slide. Where are you? Next slide. Oh, next slide decided it wanted to. Oh, there it is. Formula for one sample t-test. Okay, let's just take a look at the formula for a one sample t-test. Okay, you should be able to kind of decode from this some pretty recognizable characters here. The first thing that you would probably want to notice is that there is a X bar and a mu for the numerator. So you've got X bar and you've got a mu, okay? That's part of what we're trying to determine to find the t-value. Now notice what's unique about the denominator here. It's actually a fraction. This is really the first time we've ever seen a fraction be the denominator for a formula or an equation. So just take a look at this, and again, you shouldn't have, I don't think, any problem recalling what these mean. On the numerator part, you see that it's the X bar, and then you see you're going to subtract you're going to subtract the mu from the X bar. That's your numerator. And then you're going to see as the denominator plays out, the S stands for the standard deviation divided by the square root of, and again, here we are, n is your sample size, minus 1. So your sample size is going to vary, as you know, but here we go. I threw up a one sample example. See how it rhymed, one sample example? The only thing that's a little bit different here, and it really depends on your book, is I want to point out that if you take a look at the denominator, underneath the square root, it says just n instead of n minus 1. For our purposes, we're going to use n minus 1. So take a look at, again, the t value here. Okay, x bar minus mu, which, again, not a big surprise, divided by, in this particular case, standard deviation divided by the square root of n. If you can imagine the square root of n minus 1, it would be 29 instead of 30. Okay, so I'm going to go ahead and let you just take a look at that and let it sink in. You can see that in this particular case, the x bar, the mean of the sample is 140, excuse me, 140, whereas the mu is a value of 100. Standard deviation is 20. That's a pretty large standard deviation, divided by the square root of should be 29. So once you flesh that all out, you're going to get a value, and that's going to be your calculated t value. Okay. The calculated t value is, of course, going to be compared to the chart in our book for the critical t values. Now, when it comes to critical t values for any of the t-tests, they're all going to share the same chart. So there's not like one particular chart for one sample and a critical chart for the two sample t-test as well. So those are the type of things I want you to know for starters. Now, I'm going to make sure that I pop on here a quiz that we can kind of check our understanding with, and it'll also help count for the attendance for today. So hope you're doing well, and I'm going to stop right there for now and let you. I'm going to let you go ahead and get on with doing some more work. I'm going to post some more samples here for the normal distribution and chi-square shortly, so you can work on those in anticipation of the quiz, or rather exam, on Wednesday. Okay, be safe out there. I'll be communicating with you as much as I can via announcements and other videos as well. So stay cool. We'll talk later. Bye.